Continuous functions are one of the most fundamental objects in all of analysis, and arguably all of mathematics and science in general. All the measurements we take only have meaning when we are measuring a continuous function, since continuity means nearby inputs yield nearby outputs. But the theory of continuity, as we see it today, is tied closely with the study of topology, a field that came to light relatively recently. Topology characterizes continuity completely. That is, a continuous function is most generally defined as a function where the preimage of an open set is itself open. Or conversely, the preimage of a closed set is closed. Now, without any experience in topology or analysis, that might seem like a bit of a leap from the epsilon delta definitions that we teach all the way back to ordinary calculus. And it's leagues away from how many mathematicians in the past thought of functions, where Lagrange in 1799 attempted to describe all of calculus through power series. Today, I'm going to walk you through what makes continuous functions special in a topological sense. And I'm going to show you how the epsilon delta definition jives with the open set definition. But most importantly, I'm going to tell you what happens when you combine the ideas of compactness with continuity. Now, the metric space approach to continuity is actually due to Maurice Frechet, who introduced it in his dissertation work. After his dissertation, he went on to the University of Poitiers and was a professor there from 1910 to 1919. And when he was going to visit the University of Illinois in the US, the First World War broke out. And in the First World War, he ended up working out on the front lines as an interpreter in the trenches, where many academics lost their lives during this period. Now, during the war, incredibly, while Frechet was in the trenches, he managed to produce as many as 10 papers during the war. When I see something like that, I sometimes wonder, what the heck am I doing with my life that I'm not accomplishing as much as these people were under gunfire? If we look at a function from a finite set to reals, we can quickly determine several things. One, the image is finite. That is, applying this function to a finite collection of inputs can only give us a finite collection of outputs. So, finiteness is a property that is preserved by all functions. Two, our function takes a maximum value. This follows since there is a largest element in any finite collection of real numbers. Now, if we make this a continuous function instead of just an arbitrary function, can we find a sort of set where it has a property that is always preserved, and also where we know that the function will always take a maximum value? Continuity is stronger than no restrictions. In fact, it's very strong. So there might be some hope to finding something. Now, could open sets be the answer? Well, we could quickly see that if f of x is equal to 1 over x, then f doesn't take a maximum value on 0 to 1. And if f of x is equal to 1 minus x squared, the image of negative 1 to 1 is the half-open interval 0 to 1, which isn't open. So open sets aren't the answer. And we can work out something similar for closed sets. It turns out the right answer, the pivotal answer, the set that the creator of metric spaces, Maurice Frechet, coined the name of, is compact sets. The closed interval 0 to 1 is compact. If you look at the image of 0 to 1 under 1 minus x squared, we get 0 to 1 again. And the image is compact. And here, f takes a maximum value of 1. Of course, a single example is going to prove anything, so we need to build up some real theory behind continuous functions and, well, compact sets. So continuity is a wonderful topic to discuss, and its interactions with topological concepts such as compactness and later we will see connectedness are really profound. In fact, compactness gives us functional analysis and even measures in a certain light. And connectedness will give us the intermediate value theorem, which I'll tell you more about next time. But if you really like to play with math and learn new concepts, I would really like to tell you about today's sponsor, and that is Brilliant. Honestly, before I started working with them, I didn't look into them all that much. I knew vaguely that they had a lot of good stuff for people learning basic calculus and algebra, but as a professor, I always thought that was cute, but not really for me. Now I really see I underestimated their catalog. There are all sorts of lessons in there that I didn't expect to find. And a lot of it is helping me contextualize a lot of modern developments that I have been wondering about. For instance, they have lessons on how large language models work, and a course on data analysis and probability. These aren't going to replace a full college course, but if you were looking to know more about complex numbers or making graphs or etc., it can help get you started. In fact, if you are struggling with a lot of these ideas in mathematics, Brilliant's lessons might be what you need to get over that hump. One thing I find fun is their lessons on mathematics history. I'm sure you've noticed that I've peppered all sorts of historical tidbits throughout my videos. I don't know why, but I always love learning more about the roots and people in mathematics, almost more than the mathematics itself. This lesson here talks about how Egyptians did basic arithmetic, which is pretty cool since they didn't have our modern algorithms for doing it. If this sounds like something you're interested in, then I recommend you give Brilliant a look over. If you are one of the first 200 people that use this link to sign up, brilliant.org/thatmaththing, then you'll get 20% off of an annual plan. And everyone can get started with a 30-day free trial. All right, thank you Brilliant for sponsoring this video, and let's get back to continuity and compactness. All right, so first thing we're going to do is we're going to show the equivalence of the definitions of continuity between metric spaces and general topology. And so we're starting off with this definition for metric spaces, which basically says that a function f mapping between a metric space x and y is continuous if for any x you choose and any epsilon greater than 0, there is some delta that depends on x such that the distance between y and x being less than delta implies that the distance between f of x and f of y is less than epsilon. Now, when we change to talking about uniform continuity later, it'll turn out that this delta doesn't depend on x and it can be chosen independently. But for regular continuity, it does. So this is what we're going to start with, and what we're trying to prove then is that if we have these two metric spaces, x and y, and a continuous function mapping between x and y, we say that is continuous if and only if for every open set A inside of y, the inverse image of A is open in x. So the pre-images of open sets are open. And that's what we're going to try to prove. So what we're going to do then is we're just going to go ahead and start by assuming that f is continuous, so we're going to show that pre-images are open. This is actually really easy to do. So I'm just going to do this with a picture. Yeah, this sort of violates the basic tenet of undergrad mathematics, but I'm just going to do this with a picture. So what we're going to do is here, we're going to have something here in y, and this is going to be our x. So what we're going to do then is we're going to go ahead and select this set A. And I'm just going to do like little dashed lines there like this. So this is all the points in x that map inside of A. We assume that this is open. So we're going to try to show that this is open. I put a question mark here because we don't know yet. And so if we want to show that a set is open, remember the definition of an open set is that every point in the set is an interior point, which means that you can basically take any point in that set and you fit a ball around it and it stays within that set. So I'm going to select some point here. We're going to select this point x. And after we select this point x, we have an image over here, this point f of x. And so what I'm going to do then is I'm going to select an epsilon that is going to keep us within this A. We know that A is actually an open set. That's our assumption. And so then this point f of x is inside of A because it came from the pre-image over here. So this is all the points that map inside of A. And now I can go ahead and I can select an epsilon. This epsilon I can make small enough so that the entire neighborhood fits inside of A just by openness. So we're going to select an epsilon that does that. So and so here this has radius epsilon. I don't know if you can make that on the so epsilon. But we know that for every epsilon we can find a delta over here that depends on x, and everything within this delta neighborhood maps to be within inside of this here. And so that basically means that all of these guys map to within this epsilon neighborhood of f of x, which means they all map to within A. So then that basically means that this is actually contained inside of f inverse of A. So this implies that f inverse of A is open. Okay. Good. So we did the forward direction of this, but remember this is an if and only if, so we have to go the other way. So now that one's a lot easier. So let's go ahead and do that. Okay. So what we're going to do then is what we have is we're trying to show that this function is continuous. So what we need to do is we need to first select some x inside of x, right? So we're going to get this guy here, boop, x. And over here we're going to have a corresponding, say, f of x. Now what we're going to do is we're going to let epsilon be greater than 0, and now we're going to try to find a delta. Now, what's really nice is that we have that for every open set in Y, the inverse image is open in X. And so this epsilon defines a very natural open set, or rather the open neighborhood in epsilon of f of x. And so what we do is we look at the pre-image, and that maps us over here. It doesn't have to be a ball on this side. It can be something like this. And so this is f inverse of the epsilon neighborhood of f of x. And we know this is open. So since we know this is open, that means that there exists some delta that depends on x that is greater than 0, such that n delta of x is a subset of f inverse of n epsilon f of x. So there's some delta that keeps us in here as delta x. And, well, since it's completely contained in there, that means that everybody in there is mapped inside of this. So, which means that the distance between, say, x and y being less than delta x implies that the distance between f of x and f of y has to be less than epsilon because it's inside of this neighborhood. And boom, that's it for the equivalence. So this shows that in the metric space case, Hausdorff's definition of continuity is equivalent to the epsilon delta definition. Ultimately, this makes Hausdorff's approach more general, since it applies to a broader collection of spaces than just, say, metric spaces. But here, we only have inverse images of open sets being open, and equivalently, inverse images of closed sets being closed. But openness and closedness are not preserved through the application of the function, as we saw through his examples earlier. Okay, so continuous functions play really nicely with compact sets, where the forward mapping of a compact set that is the set of all outputs stemming from the compact set, that image set is compact. Let's go ahead and work through this. Let's take two metric spaces, x and y, and look at a continuous function f between them. Suppose that x itself is also compact, and take the image set f of x. Now we are going to take an open cover of f of x. That is, we are starting with a potentially infinite collection of open sets in the Y topology, and f of x is in their union. Then the set f of x is compact if we can find a finite number of these open sets whose union still has f of x inside. This would be a finite subcover. Now let's take a look at the pre-image of each one of these open sets under f. Since f is continuous, we know that each pre-image is open in X. Moreover, since the collection of open sets covers f of x, the union of all pre-images must also contain X. Well, we assumed that X was compact, so that means that we only need a finite number of these to cover X, and correspondingly, we only need a finite number of the original open cover to cover f of x. Hence, f of x is compact. Okay, what we're going to do is we're going to go ahead and show that if f is continuous on a compact set, then f is going to be uniformly continuous. So this proof I'm going to show you straight out of Rudin. And so this is in Baby Rudin Principles of Mathematical Analysis. But Rudin himself is actually pulling this from Heine. He's really bad about citing where these things come from. Heine was actually a mathematician at the same university that Cantor was. And so he was one of the guys who really got a lot of this analysis started. So what we're going to do is we're going to go ahead and let epsilon be greater than 0. And so for each p in x, we're going to define this. And so this is basically our delta that is going to get us being underneath epsilon over 2 that corresponds to some fixed point p. We don't know if we can choose this to be general to cover everything yet, but we do know for each point, since f is continuous, there is some delta that if q is within p, we get f of p being close to f of q, right? But that's for some fixed p. And so what we're going to do is we're going to cover x in these sets. And so these sets are j sub p are really just neighborhoods here, but it's just really cumbersome to write phi of p over 2 every time. And so we're basically contracting that radius that we found for delta, and we're taking it down by half. And then what we're going to do is we're going to cover x like this. And so it looks like this. So we know that x is, say, equal to the union for all p in x of j sub p. Or it's a subset of it, but I mean, that is their entire domain, so it has to be all of it. And so what that tells us is that there exists some, say, p1 up to pn, for which we have that x is again equal to I going from 1 up to n of J sub P I. So now we found a finite subcover because X was compact. So this uses compactness. And the reason why we want to do this is because now we can actually select a delta based on these guys. So now we know that we have covered the entirety of X with these J sub P's, which are really just neighborhoods around each one of these PI's. And now we can just take a maximum value of this quantity here. So we're going to let delta equaling 1/2 of the minimum of phi of pi, and this is for I ranging from 1 up to n. Okay, so there we go. We have now selected a delta. Now hopefully anytime we get 2 points within delta of each other, they will stay within epsilon in the image. And so that's what we're trying to show. Let's see if it ends up working. And so now that we have this delta, we hope that whenever we have two arbitrary elements out of X that are within delta distance of each other, that their image is actually still going to be within epsilon. And that's this epsilon we specified at the very beginning. So let's go ahead and see if that actually ends up happening. So what we're going to do then is we're going to assume that we have two elements, take, say, P and Q inside of X, such that the distance between P and Q is less than delta. Now we know that there exists an M inside of the set 1 up to n, with the distance between P and PM is less than 1/2 of phi of PM, right? And this just comes from the fact that P lives in here, which means that P has to be in at least one of these guys, and then that is just the definition. So that's where we get this. And then we can use a triangle inequality to get the distance between PM and Q. And so that tells us that the distance between, let's say, Q and PM is equal to, or less than or equal to, the distance between P and Q plus the distance between P and PM. And so this is less than delta plus 1/2 of phi of PM. Right, there we go. And so what ends up happening then is that we know that delta is actually the minimum of all these phi of pi's divided by 2, which means that this is less than or equal to phi of pm. So that means that both P satisfies this and Q satisfies this for the same PM. So then what we can do then is we can use the triangle inequality somewhere. I guess I'll throw this up here. I hate doing this. And this is what we end up getting. So if we take a look at the distance between f of p and f of q, and this is what we want to be underneath epsilon, this is less than or equal to the distance between f of p and f of pm plus the distance between f of q and f of pm. Now, both P and Q satisfy this guy, right, for this being PM. So that means that each of these end up being less than or equal to epsilon over 2, and that's epsilon over 2, and then that is just epsilon. And so, there we go, that is the proof. Starting from here and then ending up over here. And this is done by Heine back in the 1800s. Probably not for general metric spaces, but for the reals, because we didn't have metric space until Maurice Frechet gave it to us in about 1907. And so, but Heine did most of his work in the 19th century. So there we go. And yeah, so we have F is uniformly continuous, which we saw is extremely important for the Weierstrass theorem. When Frechet was a child, his mother ran a boarding house for foreigners, which gave Frechet considerable facility with languages, which he capitalized on as an interpreter during World War I. Many academics were conscripted during the First World War, including Karl Schwarzschild, who discovered that Einstein's equations would lead to a black hole. Now, fortunately, unlike Schwarzschild, Maurice Frechet survived the war. He went on to do work in topology and analysis, and even worked with Johnny von Neumann. Overall, Frechet's work wasn't well appreciated in his home country in France. His work introducing metric space topology was overshadowed by the work of Hausdorff, and Frechet felt that his contributions weren't really acknowledged by Bourbaki after World War I, when they were assembling their work to preserve all of mathematics. And Frechet was nominated to join the Academy of the Sciences several times, but wasn't actually admitted until he was already 78 years old, which is really a shame for somebody who opened the door for the study of all the topology and all of the functional analysis that really came after him. Okay, so now this is the most important theorem for functional analysis. And it basically says that if you have a function that maps between a compact metric space and the reals, then f must assume some largest value. And this is important because this allows us to talk about the distance between two functions. What we'll do later is we'll take two functions, let's say, that map from some compact space to the reals, and we'll take their difference and look at their absolute values, and so all continuity is preserved through all those operations, and then that gives us what we call a norm on these functions. And so it'll tell us the distance that we define between these functions is the maximum value of that quantity. So then what we're going to do in order to get there is we're going to start with a function that is continuous over a compact set, and we're going to show that it takes the largest value inside of that x. So there's some x where f takes its largest value, right? So this is in contrast to looking at something like the open interval 0 to 1, where f is equal to 1 over x, and then it has no largest value. And so there you go. And it also takes the smallest value, but I mean, it's equivalent. We'll just flip it upside down and you get the same result. And we put our theorem that we just proved over here. And so this tells us that the continuous image of a compact set is compact. And so we're going to use that. So first of all, note that f of x is a subset of R and is compact. And so then this means that f of x is bounded, and using our real number intuition, so it's not only bounded, but there's some element in there that is the least upper bound of this set. And let alpha equal the sup of, say, f of x with x and x. Right, so that's some number and the reals. What we're going to show is that there's some way that we can actually get there. And we're going to take advantage of not only the boundedness, but now we're also going to use the closedness. So we need to make a sequence that should be converging over here, and then we'll be able to find a sequence over here that'll get there. Right? So this implies that there exists a sequence xn, subset of x, such that we can approach this alpha. So that the limit as n goes to infinity of f of xn is equal to alpha. Now, this is pretty close to what we want, but it's not quite. So what we have is, we have a sequence in x. We don't know that the sequence actually converges to anything, but we know that the image of the sequence converges to alpha by our construction. So now the next thing to do is to extract a convergent sequence out of this sequence, which may or may not be convergent. And so we're going to have what we'll call a convergent subsequence, and that convergent subsequence will then end up converging, and then that'll give us a point that actually attains this alpha. And so in order to do that, we're going to use one fact about compact sets and infinite sequences. We know that every sequence in a compact set has a convergent sequence, which means that there exists a subsequence x sub n sub m, subset of x, such that the limit as m goes to infinity of x sub n sub m equals some x inside of x. All right, so we have that. So we have our limiting point now, and what we can do is we can now just apply f to this, which will give us a subsequence over here, but this sequence already converges, so that means the subsequence is also converging at the same point. So what we get is we have that f of x is equal to the limit as m goes to infinity of f of x sub n sub m, and this is equal to alpha. So now we have this alpha, which was the least upper bound of all the points f of x. So it is the highest possible point we could possibly attain. And now what we're showing is that we actually do attain it at this limit point that we found. And so there you go. You achieve the maximum value. And the minimum value you get just by doing the same thing, but put a minus sign in front of f of x and run the whole argument again. So I want to thank you so much for watching this video all the way up to the end. I really appreciate it. Honestly, this is part of a series of lectures I'm doing to try to make real analysis more digestible, or at least give access to real analysis to a lot of people who might not have had the opportunity to take the course, or maybe you're taking the course now and you just want more clarification. And I hope I can really provide that for you. Anyway, so thank you so much for watching, and I hope you have a great day.
Hey, yeah, so I stole cardboard paper or construction paper from my children. Hey, I mean, I'm sick. I'm just trying to get this video done. And, yeah, they make open covers. It's hard work.